Hello students, now we will learn about the Laplace and Poisson's equation. So already you all know that we have determined the electric field E in a region either by using Gauss law or by Coulomb's law when the charge distribution is specified in the region. So that we have done that is you can determine electric field E using Gauss law or Coulomb's law when the charge distribution is specified in a particular region. Or also you have used the relation that is E is equal to minus del V. That is what one of the way of finding out the electric field intensity when a potential is specified throughout the region. So this is what we have determined the E by using Coulomb's law, Gauss law, or using potential. But in practical cases neither charge distribution nor potential distribution is specified only at some boundaries, means practically we are knowing the charge distribution and potential distribution is only on at some boundaries. So these type of problems are known as electrostatic boundary value problems. So electrostatic boundary value problems. So these problems now can be rectified, or these problems can be simplified by using the field and the potential we are determined by using Poisson's equation or Laplace equation. So whatever the field available at boundaries are utilized for the calculation of potential and field over the distribution. So that is done by using the Poisson's or Laplace equation. Hence Laplace equation is a special case of Poisson's equation, right? So this is about the Laplace and Poisson's equation. Why we need Laplace and Poisson's equation? Because due to some boundary value problems we need the Laplace and Poisson's equations, right? Now let us consider a linear material. Poisson's equation and Laplace equation can easily derived from Gauss equation, that is del dot D is equal to rho V. But what is D? D is nothing but epsilon E. Now putting the value of D in the Gauss law, we get del dot into bracket epsilon E is nothing but equal to rho V. So from the homogeneous medium for which epsilon is a constant, so we write del dot E is equal to rho V by epsilon. Also E is equal to minus del V. The previous equation it becomes what? Put E is equal to minus del V in the previous equation. So del dot into bracket minus del V is equal to rho V divided by epsilon. So del dot del V is nothing but equal to minus rho V by epsilon, right? So now del square V is nothing but minus rho V divided by epsilon. So this equation is known as Poisson's equation, which states that the potential distribution in a region depend on the local charge distribution, right? So that is del square V is nothing but equal to minus rho V by epsilon is nothing but Poisson's equation. Now in many boundary value problems, the charge distribution involved on the surface of the conductor for which the volume charge density is 0, that is rho is equal to 0. So in that case Poisson's equation reduced to del square V, that is nothing but equal to 0, Means in some boundary value problems the charge distribution involved on the surface of the conductor for which volume charge density is 0, so therefore the Poisson's law is reduced to this equation, that is del square V. So this equation is known as Laplace equation. So hence we have discussed about why we need Poisson's equation and Laplace equation, and also we have defined the Poisson's and Laplace equation, and we have derived the equations of our Poisson's and Laplace. Thank you.